Hi everyone, welcome to my talk, Securing CI/CD Pipelines, Exploring Vulnerabilities in Workflows. I'm Siddharth Murali. I'm currently a third year PhD student at Purdue University. I'm a member of two labs, PERSEC Lab and PERS Lab. My research mainly focuses on various aspects of system security and trying to apply techniques such as fuzzing and static analysis on various domains. I'm also a semi-active CDF player. I play CDFs occasionally with Shellfish and sometimes with my undergrad team, BIOS. So in today's talk, we'll be going through some of these common CI/CD concepts, and then we'll be taking a deep dive into the GitHub Actions CI platform. We'll be looking at what are the command injection vulnerabilities that are present in the GitHub Actions platform. And we'll be looking at Argus, the solution that we developed to find these vulnerabilities. And finally, I'll wrap up by giving you some tips on how to secure your GitHub CI pipelines. So what are CI/CD platforms? So continuous integration and continuous development platforms are basically platforms that play a huge role in software development life cycles these days. So they automate a lot of these common tasks, such as build, test, deploy. So whenever you have a code base, it can automatically build these for every update, such as a commit. And then they also integrate these like unit tests and security tests into the cycle, so you can run these tests for every build. And if you want to automatically release updates to your software, you can also do that using these pipelines. So before we dive into the vulnerabilities, let's get familiar with some of the basic concepts. So these components might go by different names depending upon the platform we are dealing with, but the core concepts and the ideas remain basically the same. So the first is the source repository. So the source repository basically consists of two parts. The first part is basically the code, which contains the source code of the application that you're developing. And the second part is the corresponding metadata, which keeps track of the history of the changes that you've made during development. And it also has like additional stuff such as commit messages, names and email IDs of authors, and things like that. So CI platforms allow developers to define their pipeline using a declarative form that's called a workflow. So this language varies based on the CI platform, but commonly workflows contain multiple jobs. Each of the jobs will contain multiple steps. Like for example, you might have a build job, and the build job might have multiple steps, whereas there one step you try to install all the dependencies, the second step you try to build the application, and the third step you try to verify that the build is fine. And this is, this is referred to by different names, but the core idea always remains the same. Now, since a lot of these CI pipelines, they perform the same set of tasks, the CI platforms usually have something called plugins. So these are basically commonly repeated tasks encapsulated into form of an application that you can use as a part of your CI pipeline. So we can classify plugins into two types. We can say there are built-in plugins, which are basically plugins that are created and maintained by the CI platform itself and perform maybe the most common tasks that they have seen or interact with the APIs of the CI platform itself. And the other type is basically third-party plugins. So these are written by developers on the internet and open source so that any user can actually use it. And most platforms also maintain some sort of a directory so that these third-party plugins can be found by other developers. Now, once you have, as a developer, you have configured a workflow, now you need to determine how you run the workflow. So this is based on webhooks or events. So you can define webhooks or events which kind of trigger the execution of the workflow. These might be events such as, say, pushing code onto the repository, submitting pull requests, creating issues, etc. And the amount of webhooks and the types of webhooks depend based on the CI platform. And the final component that we'll discuss here is the runner. So the machines that run the CI pipelines are called the runners. So they usually have some sort of an agent installed, which will parse the workflow and perform the steps. So they can be either provided by the CI platform itself, or you as a user can kind of self-host them. So as you can see, this is from GitHub. So GitHub provides like various options of having like Windows, Ubuntu, and Mac OS machines to run your pipelines on. Now for this talk, we'll actually be looking more deeper into a platform called GitHub Actions. So GitHub Actions is a CI/CD platform that was developed by GitHub and released in 2018. So it has various features that makes it very popular. So in GitHub Actions, developers can define these workflows, which is the CI pipeline. They have actions, which are plugins that have these commonly repeated tasks. GitHub also provides a marketplace through which you can see all of these actions. And all of these workflows are event-driven, so they interact with a lot of GitHub APIs, such as pull requests, issues, etc. So now let's look at how a common workflow looks like. So on the top, you can see the triggers. These triggers determine the events on which the workflow is run. Here, the workflow is run on a pull request when the pull request is opened. So each workflow, again, consists of multiple jobs. These are usually independent tasks, so they are run in different virtual machines. And inside each of these jobs, you can define a bunch of steps. And these steps will get executed sequentially. So now, since these jobs and steps are kind of independent, so to share data among them, you need to use outputs and environment variables. GitHub also allows you to define dependencies for jobs. So a job only executes after all of its dependent jobs have finished execution. And finally, GitHub provides the ability to access event data, such as titles of pull requests, stuff like that, using these special variables. Now, inside a workflow, you can also reference actions. So actions can be of three types. They can be of JavaScript, where the functionality of the action is developed in Node.js. You can see the Node.js files referenced there. Or they can be of composite nature, where they have a similar YAML file with similar syntax as workflows. And these composite actions internally can also call other composite actions and JavaScript actions. And the last type of actions is Docker actions, where you can just have a Docker container which performs the tasks that you need to do. Similarly, workflows can also use reusable workflows, which are basically similar workflows stored in a different file. These workflows can also use actions, composite actions, JavaScript actions, and they can also use other reusable workflows. So now let's come to some important properties of these GitHub Actions platform. So GitHub provides a variety of triggers. So these triggers can be used to configure when the workflow needs to be run. For example, here the trigger is basically when an issue is opened or edited. One important fact to note is that when a workflow is triggered from an external fork, such as a user forks a repository and then creates a pull request, and then the workflow is triggered, then if you are a first-time contributor to that repository, then your workflow does not run automatically. You need a maintainer to approve the workflow to be run. This is because GitHub faced a lot of crypto mining issues, where people used to just submit pull requests with crypto mining software, so they added this protection. However, if you have already contributed to the repository, your workflow just starts executing immediately. The second important feature is the permissions. So whenever you have a workflow, GitHub provides you with a GitHub token, which is used to authenticate with the GitHub API and used for things such as committing code back to your repository, creating issues, and such stuff. Now, since these permissions are usually dangerous, GitHub provides a mechanism for workflows to kind of restrict them. Such as in the example here, the workflow is used to deploy static content to pages. So the workflow does not require write access to the contents of the repository, but it requires write access to the pages scope and the ID token scope so that it can deploy the content onto the pages. Similarly, when the workflow is triggered from an external fork, if you have a trigger that is basically a pull request trigger, you are only given a read-only token. So the token has only read scope by default to all of the parameters. However, if you as a developer, you need to have write access, like you need to have write permissions on the GitHub token, then you need to use a special trigger known as pull request target. And the final feature that we're going to discuss is called secrets. So secrets allows you to store key value pairs for sensitive information, such as you want to store your API keys for, say, AWS or SSH private keys on the workflow, and then use them. So, like for example, in the case here, you have a workflow where you are trying to clone another repository. So now to authenticate to that repository, you're using an SSH private key. So now you cannot directly store the SSH key inside the workflow, which is considered insecure. So you need to store it as a secret, which gets replaced when the workflow is run. Again, based on the trigger, so if you have a pull request trigger, the secrets are not passed to the pipeline by default. So if you as a developer want to have secrets, then you need to use this special pull request target trigger. So based upon all of these things, we kind of came up with a threat model where we defined like what an attacker should not be able to do and what compromises the CI pipeline. So we kind of referred to all the OWASP guidelines for CI/CD pipelines, and this is what we came up with. So the attacker should not be able to execute arbitrary commands in the pipeline without corresponding visible code changes. The attacker should not be able to gain an access to the read-write GitHub token for the repository, because he can use it to commit code back into the repository. And finally, an attacker should not be able to leak the secrets that have been set by the developer in the pipeline, because say, for example, you have an AWS key, the attacker can use this maliciously for their things. So the motivation for us to kind of look into this research was basically a blog post that we saw from the GitHub security team by Jaroslav, where he introduced this idea of command injection vulnerabilities in GitHub workflows and actions. And this blog post kind of motivated our interest into looking into this domain. So now let's look at what is a simple motivating example for a command injection bug. Say you have a workflow here, and the only step inside this workflow is basically you want to log the title of an issue. So you have the command where you have echo, and then you are using this special CI variable which contains the title of the issue. And as you can see, when someone creates an issue, such as the issue title "My First Issue" here, the text gets replaced, and you are now echoing "My First Issue." However, this can be misused by an attacker, where an attacker can create an issue with like a malicious title. And here, as you can see, the echo command is ended, and then the attacker has the ability to execute arbitrary commands on the pipeline. This is a very simple example of how a bug can look like. So first, let's look at what are these attacker-controlled inputs. So the first and the most common one is basically GitHub event information. So anything such as GitHub issue titles, GitHub issue body, or pull request titles, pull request body, they're all controlled by an attacker. Similarly, Git metadata, such as commit messages, authors' names, emails, they can also be controlled by an attacker. Other things that an attacker can control include file names, because GitHub allows for all set of characters inside files, and similarly, content of the file. So if you are processing based on the content of a file, that can also be controlled by an attacker. So I have a full list of the 10 sources here, the attacker controlled inputs. So now we were actually looking at tools which can find these vulnerabilities. So at the time that we were looking, we basically figured out there were 2 tools that try to figure this out. So the GitHub security team developed a CodeQL query, which basically parses the workflow YAML and then just does a regex search inside the run command to see if any of these attacker-controlled inputs are directly being used there. However, this feature was kind of coupled with their JavaScript language queries, which made it possible only for JavaScript repositories to kind of run and do this analysis. Another tool that we saw was GAST, which is basically developed from the University of Genova, and they basically tried to do the same approach where they use regex matching to figure out the presence of these attacker-controlled inputs. And these were targeted to run basically on Python repositories. Now, by just looking at these solutions, we were kind of sure that these aren't efficient to detect the sort of command injection bugs that we want to detect. So the reasons are, 1, these tools aren't aware of the workflow semantics or how the workflow gets, the execution flow of the workflow. These tools cannot track data flow across workflows, the reusable workflows used by them, and the actions that are used by those. So it's just doing a regex grep on the workflow itself. And because the platform, the ecosystem, uses a lot of programming languages, it's not very easy to develop a regex-based technique to figure out to pattern match inside all of these different programming languages. And finally, since you have all of these permission, secrets, and all of those, so the impact of a vulnerability is varies a lot depending upon all of these parameters. So these tools cannot predict the potential impact of these vulnerabilities. So to solve all of these issues, we presented our solution, which is basically Argus. It's a staged static taint analysis tool for GitHub workflows and actions. So now let's look at how we designed Argus. So the first step for Argus is basically to generate action taint summaries. So whenever we have actions that are used inside these workflows, we want to generate taint summaries for each of them and then store them in a specific database. Then we want to take each of these workflows and then convert them into a corresponding workflow intermediate representation that we developed from scratch to represent CI/CD pipelines. And once we have this intermediate representation, we try to run it with the static analysis engine that we developed. So whenever the workflow references an action, the static analysis engine tries to get the action from the taint summary database. Finally, from the reports that we've generated from the static taint analysis, we feed it into an impact classifier, which basically spits out the warnings and gives you the impact for each of them. So now let's look at how we generate taint summaries for actions. So we try to figure out 3 types of taint flows. So the first type of taint flow is direct flow, where the taint originates inside the action and then flows into a sink inside the same action itself. The second flow is an input flow, where the taint originates from a workflow and flows inside an action and then goes into a sink inside the action. And the third type of the flow is the output flow, where the taint originates from inside the action and then flows into a sink inside the workflow. So for figuring out all of these taint flows for each type of actions, we developed plugins for each type of actions. So far we support JavaScript actions and Composer actions. We do not support Docker actions as of now. So now let's dig deeper into what we did for the JavaScript actions. So first we need to create, for doing taint analysis, first we need to create taint sources. So the taint sources that we defined for JavaScript actions is basically any function that gets input from the workflow, any environment variables that are used, that are read from inside the action, and any sort of GitHub API, such as issue titles that are accessed inside the action. Similarly, we define taint sinks. Taint sinks are output functions which can be used to set output for the next step. And similarly, dangerous Node.js functions such as eval, exec, spawn, etc. And to perform this sort of analysis on Node.js, we used GitHub's static code analysis tool called CodeQL. We developed custom queries based on the requirement in CodeQL. So now let's look at simple examples for all of these various flows. So as you can see, here is an action that's written in JavaScript. If you see, there is a taint source issue title that is being used inside a function called renderMark, and later the same issue title is being passed inside an exec command. So this leads to a command injection vulnerability, because as a user you can control the issue title and you can use it to execute arbitrary commands. So any workflow that uses this action will be vulnerable to command injection. So this is a direct flow. The second type of flow is basically input flow. So here you have functions such as getInput, which takes input from the workflow and feed them into parameters like dangerous function calls such as exec. So here, if the attacker gets control on the parameters such as the property and value, then he can use it to execute arbitrary commands using the exec. So not all workflows using this action are vulnerable to command injection. However, if you have some sort of a workflow where you pass either property or value with some sort of malicious input, then it ends up being vulnerable. The third type is the output flow. Here you have an attacker-controlled input such as command body, which is being used to set as an output. So this output is being passed back to the workflow. So now if the workflow does not use it properly, then it can lead to a command injection bug. So here, as you can see, any workflow that uses the command body output in a vulnerable manner basically ends up causing a command injection bug. Now, we do the same steps to identify taint sources and sinks for composite actions. And the taint sources that we identified, again, are all of the input sources. We also figure out the context variables, which are basically all of the attacker-controlled inputs that we discussed earlier. And then we also taint all of the outputs that are coming from the actions inside, like tainted outputs that are coming from the actions inside. And the taint sinks are basically the run keywords that are present inside the commands, the outputs of the actions, and the action sinks. And since there is no existing taint engine that can handle workflows, we developed our own YAML and bash taint engine that operates on the intermediate representation that we created. So for each of the composite actions, we converted them into the corresponding intermediate representation and then ran it with our taint engine. So again, let's look at some of the real world bugs that we found. So here is an example of a direct flow vulnerability. Here, as you can see, the github.headref, which is basically an attacker-controlled input, is being used inside a run command. So it's directly being used inside a run command, so the attacker can use it for a command injection bug. So any workflow, again, using this action will be vulnerable to command injection. The input flow. So now for an action, you can define what is the input for the action. Here you can see that there is an input named title, and below you can see that inside the run command, the title input is being used directly. So this again leads to a command injection vulnerability. However, as we discussed earlier, only the workflows that pass tainted input to the title parameter will be vulnerable to command injection. again, output flow for YAML actions. Here you can see that in the command they are using the headref as an output, and then the headref branch output of the action is now tainted. So any workflow that takes this output and then uses in a vulnerable manner is again vulnerable to command injection bugs. Okay, so that's it with the action step. Now let's look at how we generate the corresponding IR. So we try to develop a platform agnostic intermediate representation which can capture different semantics of a CI pipeline or a CI workflow. So here we try to capture various features of the workflow, such as execution ordering, execution environment. As you can see, it defines what type of action it is, and then captures all the environment variables that are being passed to the action. And we also try to capture all of the CI variables that are present in the action. Once we have the corresponding IR, we try to develop something called as a workflow dependency graph. So here, since jobs inside a workflow can have a lot of dependencies, we kind of create a graph based on the dependencies. And if a job is using a reusable workflow, we also combine the graph of the reusable workflow with the original graph of the workflow. And this basically gives us an order in which the workflow will execute. So now that we have, for every workflow, we have an IR and a workflow dependency graph, we run a taint engine with these features. And whenever the taint engine needs or encounters an action, it queries the taint DB and gets the corresponding taint for the action. And if it notices any flow from a source to a sink, it creates a vulnerability report. Now, how do we classify these reports? So we classify reports into three types: high impact, medium impact, and low impact. So the high impact vulnerabilities are vulnerabilities where the attacker, without any sort of maintenance interaction, can exploit the workflow and then gain access to the read-write GitHub token or secrets present inside the workflow. So for example, suppose an attacker can just open an issue and the workflow will automatically execute and the attacker gains access to the tokens. So medium impact is basically where the attacker has access to the read-write tokens and secrets, but requires some sort of maintenance interaction for the workflow to execute. Say for example, an attacker creates a pull request and the workflow only executes after the maintainer merges the pull request. So there is some sort of a maintenance interaction required for the vulnerability to execute. And the final type is where low impact, where there is no access to the read-write GitHub token or secrets, no matter how you try to exploit the vulnerability. This is when the vulnerability is inside a pull request workflow, and it's always passed. It's always passed with a read-only token and no secrets. So while doing the study for the impact, I discovered an interesting policy violation which allows attackers to increase the impact of certain attacks. So as we know, for pull request workflows which are triggered from external forks, GitHub automatically lowers the permissions to read-only. So the vulnerability by default has only a low impact. But I noticed that when a pull request is created between two branches of the same repository, then an attacker can, then the workflow runs with higher permissions. So now I noticed that for GitHub repositories with more than one branch, an attacker can create a pull request between two branches inside the same workflow. And the only requirements for this are you need to have like a non-empty title and a body. And the benefit of this is basically an attacker can trigger a workflow with higher privileges without any sort of contributor access to the repository. The workflow runs without any sort of maintainer approval, even if the attacker is a first-time contributor. Both secrets and read-write GitHub token are present by default if the workflow has not specified permissions. However, an attacker can only control pull request title and body directly. He can control other parameters in an indirect way by submitting a pull request, getting it accepted, and then creating another pull request. So we reported this vulnerability to GitHub. GitHub fixed the vulnerability because on high priority, and they also made a listing on it. So based on all of these parameters, we created an impact classifier. So if a workflow has a GitHub token with write permissions, or it has secrets inside the workflow, then we process it. If it has neither of these, we say that it's a low impact vulnerability. So now, assuming that a workflow has both of these, we try to look at the trigger. So if the trigger is not a pull request trigger, then by default the permissions given to the GitHub token are read-write. So we classified it as high. However, because of the vulnerability that we found earlier, if it's a pull request and then it's the title or the description that is tainted, then an attacker can control that. So it's again classified as high. However, if it's none of these parameters, then it requires some sort of a maintainer interaction for the attacker to gain access to it. So we classify it as medium. The only special case is when it's a headref. Headref is basically the name of the branch. And since an attacker cannot control the name of the branch when he's creating a pull request, we classify that as a low impact vulnerability. So now let's look at a case study which will allow you to understand more about the types of vulnerabilities that we found. So this is a very interesting one that we found in an open source repository called Dynamo, which is a very popular repository with over 1,000 stars and 500 forks. So now let's dig into the workflow. As you can see here, the workflow is basically triggered when issues are opened or edited. So this is the vulnerable job in question. So now let's look at it step by step. So in the first step, you can see that it's trying to check out the action. In the second step, it has a step which is named remove conflicting characters. And as you can see in the environment variables, one of the inputs that we looked at earlier, the issue title is being used. Now the same environment variable is being passed to another step as the parameter, as the argument to an action. As you can see now, the string argument contains the issue title. So the string argument basically is from the action replace string action, which is a JavaScript action. So now Argus tries to query the DB for this action. So as you can see from the DB, the input named string flows into the output named replaced. So in the next step itself, you can see that the output named replaced is directly being used inside a run command. So now an attacker can use an issue title to create a command injection vulnerability. Now what can an attacker do? An attacker can use this to exfiltrate secrets. So in the very next step itself, you see that there is a secret called Dynamo bot token. So now we had a working tool. So now we need to figure out a data set. So we wanted to collect a lot of open source repositories which use GitHub workflows. So what we did was we went to GHArchive and then wrote a query where we tried to search for any sort of events that were created by the GitHub Actions bot. And then we wrote a script to get all of these workflows that are active for the last 2 years and stored them all into a MongoDB. So in the end, we ran the collection script for more than 2 weeks because of all of the GitHub rate limiting. And we got around 2.8 million workflows and 1 million repositories. And we ran Argus on all of these. So here are the results that we got from running it on all of these. So as you can see, we ran Argus with just the taint summary mode. And we noticed that there were over 10,000 actions that were vulnerable to an input flow. So any workflow that uses, that passes tainted parameters to these actions would lead to vulnerabilities. It's interesting to note that this is more than 15% of all the actions that we got from GitHub. Similarly, we found also 136 direct flow actions. If you use any of these direct flow actions in your workflow, by default, your repository is vulnerable to command injection bugs. So now we also try to evaluate the precision of our taint analysis. So we manually went through the taint flows that we discovered, and then we noticed that we have a 94% precision in JavaScript actions and around a 96% precision in composite actions. And now we wanted to evaluate it on the workflows. So we ran it on all the 2.8 million workflows, and we identified around 27,000 vulnerable workflows, out of which around 3,600 workflows were high impact vulnerabilities, which means that without any sort of maintainer interaction, an attacker could get access to the tokens or secrets inside these repositories. Again, to identify the precision and the number of vulnerabilities, we kind of got all of the high vulnerabilities, the 3,600 ones, and then we manually verified the presence of these vulnerabilities. We also sampled 1,000 vulnerable workflows, both medium and low, and then manually verified the presence of these vulnerabilities. And we noticed that Argus has a precision of 93% in identifying these vulnerabilities, and it found more than 5,000 zero-day vulnerabilities. So now we have 5,000 zero-day vulnerabilities. We have no clue how to report all of these vulnerabilities. We cannot create pull requests, because you can create a pull request and an attacker can kind of, in the gap, try to exploit these vulnerabilities before the maintainer accepts these pull requests. So because of this, we tried to reach out to the GitHub security lab, who kind of advised us on how to report these vulnerabilities. So we used GitHub's private vulnerability reporting feature, where the report is basically private and can only be viewed by the maintainers. So we automated the process again. We started checking whether repositories have security policies defined. A lot of them did not. And then if they have the private vulnerability reporting feature enabled, we started creating reports. If they did not, then we open an issue asking them to enable the vulnerability reporting. Once it's enabled, we create vulnerability reports for them, and then we work with the developers to fix them. And this was a massive undertaking. However, even after following all of these measures, our GitHub accounts still got blocked around 4 or 5 times during the procedure, because there was some or the other person who was trying to report us because they did not like the method that we used. So in the end, we created more than 1,800 issues, out of which more than 250 users responded. It's still an ongoing procedure. Now, once someone enables the vulnerability reporting and they notifies that they have enabled it, we started creating reports. We worked with developers to fix more than 150, and in the end, we ended up getting around 20 security advisories. These were mainly for the actions. We did not ask for security advisories for the workflows. GitHub security team played a huge role in helping us find these bugs. We did a coordinated disclosure policy with them, and they also published blog posts validating our research and basically giving a few tips for the users. And in the last segment of the talk, I'll try to elaborate on these tips. So what are the limitations of Argus? So Argus does not support Docker actions, which kind of compose like 30% of all the actions. It inherently has all the static analysis limitations that it inherits from the static analysis tools that we use, such as CodeQL. And so far, we do not have support for other CI platforms. It's currently in progress. We are also looking for support from the community to help us develop support for other CI platforms. Okay, before I conclude, let's quickly look into how you can secure your GitHub workflows. So there are 4 things, in my opinion, that people should really take care of. The first one is basically handling untrusted input. So if you want to use any of those inputs, such as the attacker-controlled inputs that we discussed earlier, then you should not directly use them in run commands inside your workflows. Instead, you should have some sort of an intermediate bash variable that you can use for running these commands. A second and very important thing is you should always audit your third-party actions. One of the vulnerabilities that we discovered was inside a repository from VMware with over 2.2K stars. This repository from VMware had a workflow that had no stars. It's just a simple work in progress workflow written in bash, which was vulnerable to a direct flow vulnerability. So the main repository was also vulnerable to the same repository. So you need to always audit your third-party actions as much as possible. So now, when you have an action, you can refer to it in three ways. You can either use an indirect access, where you use a tag present in the GitHub repository, or you can use it branch name, such as master. However, if the action gets compromised, then whenever you rerun the workflow, you can get a malicious version of the action. So instead, you should always pin your GitHub actions to commit hashes inside the workflow. This, however, leads to another issue. So you might need to update your actions to receive security updates. You always need to make sure that even if you have tagged it to a specific commit, whenever there is an update, you should probably audit and update. Finally, about permissions. So because if your workflow was created before February 2023, when GitHub changed their policies, you by default for any workflow receive a read-write GitHub token. So you should always modify the token to be read-only and isolate the permissions of the GitHub token at the job level. So I'll also present some tools that can help with this. So GitHub Security Lab created an advisory action which basically monitors the workflow and suggests the least permissions that are required for your workflow. So you can just use that action and then use the same permissions that are recommended by the action. I'm also, whenever I use workflows, I use the hardened runner for workflows. This is basically a modified runner which blocks all outgoing traffic and detects changes to source code, etc. There are some static analysis tools as well. You can use our tool, which is packaged as a Docker container, which can identify these command injection vulnerabilities. We also submitted a lot of our queries and our code to GitHub and integrated it into GitHub's code scanning. So you can also enable that onto your repositories to get an idea of these. Okay, to summarize, in this talk, we kind of discussed core CI/CD concepts. We also introduced Argus, which is the static taint analysis system, the first static taint analysis system for GitHub Actions. We also introduced the taint summaries for actions and our workflow intermediate representation. And that's it for my talk. I would like to thank my collaborators from Purdue University and North Carolina State University who helped me with this research, and also GitHub Security Lab who helped us report all of these vulnerabilities and awarded us a lot of bug bounties as well. Thank you.